Okay, 5D is about sector area. So area instead of arc length. Again, theta over 360 times pi r squared is the fraction of a circle in degrees times pi r squared. Well, if instead we thought of this in radians, we would have 2 pi. And what would we be able to do? The pi's would cancel. And r squared theta over 2, typically we say half r squared theta, where theta is measured in radians again. Okay, so one more time, the formula is arguably a little bit easier in radians. While we're here, we could also talk about segments. So what is a segment? A segment is made by a chord. So imagine a chord on a guitar, those strings that go over there. It creates sort of this kind of shape. This is called a segment. A segment, you can think of a segment as a sector minus a triangle, okay? And then that will leave this part here. That's what's going on. So it's probably not too surprising that we take a sector, the area for a sector, the formula for it. This one here, now this might look unfamiliar, but this is actually half AB sine C, written slightly differently. Now, A and B are the same, so you get sort of half r squared, and instead of C, you're talking about theta. So actually, this is something just written in a slightly different way. Sometimes you can sort of remember it in this form here. Why would you do that? Well, it's a little bit quicker, okay? And that directly tells you a segment if you want a segment. So it's quite important here to make the distinction between a sector. A sector is typically larger, okay? It's from the center of the circle out, okay, and up to the circumference. A segment is a thinner part. It's got a curved part there. It's made by a chord. It has that straight line that cuts it off. Let's do some examples. The area of minor sector. Minor sector means it's this part. Major sector would be this part. Sounds simple, but loads of mistakes get made on that. So please make sure that you don't fall for that one. So half r squared theta. That's what we're looking for sector area. I'm using A for sector area here. Sector area is 28.9 equals half r squared, and I know the number 0.8. Can you see r is the only unknown there? So I can use inverse operations to find out r. I know it's solving an equation, and if you solve in general x squared, you should have two solutions. It should be plus or minus. However, radius is distance. Distance is a scalar quantity. Positive only, please. 8.5. A plot of land is in the shape of a sector of a circle of radius 55. Okay, so we've got R. The length of fencing that is erected around the edge of the plot. Around the edge of the plot. To me, that sounds like perimeter. Calculate the area of the land. Okay, so half r squared theta. Got r. I've got r and I need theta. So what am I going to do here? Because I need a and I need r. Well, if I have r or theta, what have I not used? I haven't used the 176. So 55 plus 55 is 110. That leaves 66. This is the L part, if you remember the arc length. Arc length is r theta. 66 equals, well, the radius is 55 theta. So can you see here, 66 over 55? Okay, what's that? 6/5? Okay, equals theta. Divide top and bottom by 11. So 6/5 equals theta. And now I can put it in here. So the area is half 55 squared times 6 over 5. 1.2 you might expect to see. 6 over 5 is 1.2. So here we're starting to do what's very, very common, is we're combining the arc length and the area of the sector together. expect lots of questions like that. With segments, so what could we do with segments? Do we remember? You could do half r squared theta minus sine theta. If you can remember that, well done. You will save yourself lots and lots of time. So find the area. The area of a segment this time is equal to half times 4 squared. Okay, I don't have theta. So again, I need to do some problem solving. That's 4 and that's 5. Choices. So you have choices. You could split this down the middle. Because it's an isosceles triangle, it will create right angle triangles. So you could use 2.5 and 4. And this is the opposite in the hypotenuse. So inverse sine in radians mode of opposite, which will be 2.5 over 4. This will give you theta. And can you see from there, theta and sine theta, you would be able to solve that. Okay, they've decided to use the cosine rule here, which is fine. That's up to them. But you could have used SOHCAHTOA instead. If you have circles, you get lots of isosceles triangles. Isosceles triangles broken into 2 will give you right angle triangles. Okay. What have we got? One final example here. I will come to this one later because this is actually quite a tricky example, this one here. Let's do the test your understanding first. So pause the video, have a quick go at the test your understanding. Okay, so find the area of the sector. Now you need to sort of spot that this 9 is turning around and is the same 9 here. You need to be able to spot that that's a sector of a circle. Obviously, they have given you quite a few clues in the question here as well. So half r squared theta, we plug the numbers in. The line AC is perpendicular to OA. Find the length of AC. So some general problem solving here. How do we find this length? Well, I would use SOHCAHTOA. So angle, side, side. Opposite the right angle is the hypotenuse. So opposite and adjacent, I'm expecting tan here. Okay, so we can use tan to find this opposite side here. And then generally a good idea to write the answer a newfound line or angle on because it might come in the next part. The region H is bounded by curve AB, yes, and AC and AB, okay. What is this part here? Well, think about a large shape first and then subtract things off is generally the best way. So I'm looking at this and I'm seeing a triangle that needs to have a sector removed. Well, I know what the sector is. It's 28.35. Do I know what the triangle is? No, but I could work that out. Could you do something complicated? Probably, but look, it's a right angle triangle. Let's be sensible. Let's save time. Base times perpendicular height divided by 2. So if you just do 7.58 times 9 over 2, and then you subtract this number, you should get the answer, 5.76. Okay, I said we were going to finish with this one, so here we go. If we have space. So AB is the diameter. Given the AOC is 3 times the shaded segment. Okay, AOC is 3 times the shaded segment. That sounds important. Show that 3 theta, right? So everything is in general terms. So what would be a good place to start with? I want to talk about the segment so I can set up an equation, and I want to talk about the triangle so I can set up the equation. So AOC is 3 times, I'm just going to write segment. What's the segment? Well, the segment in general terms is half r squared theta minus sine theta. What's AOC? Well, that is 180 which is pi. That's pi minus theta, isn't it? That angle there is pi minus theta because they got to add up to pi. The area of a triangle, so is half r squared sine theta. So it's going to be half r squared sine of not theta, but pi minus theta. Now, if you know your identities, pi minus theta, so think about like 30 and 150, they're the same thing. So that can actually be written as that. So I think we're pretty close already. So half r squared sine theta equals, let's put all the parts that are the same at the front. R squared times 3 theta minus sine theta. I know this is a bit messy. Then we can do loads of cancelling out, which makes sense because the final answer doesn't have any r in it. And do you want to just pause and have a go, seeing if you can finish off the answer from there? So you can actually expand out this bracket on the right-hand side. Why are you allowed to do that? Because it's just a number on the front. So it's just sort of about multiplying each of the parts here inside, each of these terms, by 3. So sine theta equals 3 theta minus 3 sine theta, rearranged, and there we go. That's a bit of a tricky one, that one there. So arc length is being used also on questions about the area of a sector, which is half r squared theta, and we can also link it with other things we know, such as areas of triangles, symmetries of sine, and general problem-solving techniques that we've seen before with geometric problems. And that takes us up to exercise 5D.